We're now going to take a look at partial limits, also known as left and right-hand limits, and compare them to full limits. So to illustrate what a partial limit is, we're going to take a look at an example. Let's consider this function f of x equals x plus 1 for x larger than 2 and x squared for x less than or equal to 2. Now down here we have a graph of this piecewise defined function. And we want to ask ourselves this: what is happening to the function values f as x approaches 2 from the right-hand side and from the left-hand side? So let's let x approach 2 from the right-hand side first, and we want to see what are these function values up here approaching on the y-axis. So keep an eye on that red dot on the y-axis. So now, as x is approaching 2 from the right-hand side, notice that the function values, they are getting closer and closer to the number 3, right? So we see here, as x is converging to 2 from the right-hand side, written like this, notice x converges to 2 with that little plus right there, we see that f of x is getting closer and closer to 3. Now we call that a right-hand limit, and we denote it like this. Notice we write limit x converges to 2 with a little plus there that indicates x is approaching 2 from the right-hand side. F of x is approaching 3. So the limit, right-hand limit, is 3. Now notice we could evaluate this. We looked at it graphically and determined what the 3 was. Well, notice we could have evaluated that by just writing limit as x approaches 2 from the right of f of x equals, now what we can do is we can just put in x plus 1 for the f, because we know that when x is larger than 2, the function f, if you look up here, it's equal to x plus 1 when x is larger than 2. So we put that in place of the f. Now with this piece right here, with this limit, we can just plug the 2 in for the x. 2 plus 1 is 3. And there you go. This is what we call a right-hand limit. Now let's see what's happening as x approaches 2 from the left. So once again, keep an eye on this red dot right here on the y-axis, and let's see what it's approaching as x approaches 2 from the left side. So as x gets closer and closer to 2, notice that the red dot, the function value, that is getting closer and closer to 4. So we see that as x is approaching 2 from the left, f of x is approaching 4. And we have that noted down here. So we see that as x approaches 2 from the left side, and we write that like this. Notice the notation, x converges to 2 from the left. That little negative superscript means x is approaching 2 from the left side. F of x is approaching 4. We call this a left-hand limit, and we denote it like this. Limit as x approaches 2 from the left of f of x equals 4. Now notice we can evaluate this 4. We looked at it graphically up here, but we could evaluate it by just writing limit as x approaches 2 from the left equals limit as x approaches 2 from the left of x squared. Notice that for x less than 2, f of x was defined to be x squared. Just look back up here at the way the function was defined. You see up here, notice how the function is supposed to be x squared when x is less than 2. So we can just substitute the x squared in for the f. Then we're just evaluating a limit as x is getting closer and closer to 2 from the left of x squared. Well, we can just put that 2 in for x, and we get 4. Now what about the full limit as x approaches 2? Well, the full limit of f of x, that does not exist, because f of x is not approaching a single number L. For your full limit to exist, your function has to be approaching a single number no matter which side x is approaching the limiting value from. In this case, f is approaching 2 different numbers, 3, and 4, and so we have to say the full limit does not exist. So we have this result now. In order for the full limit to exist, we need the left and right hand limits to exist, and they must be equal to each other. So let's illustrate that concept with the function down here. So all we did is we took that function above and we just changed it a little bit. So now we're going to look at the left and right hand limits of this function and see how they compare to the full limit, and see if the full limit exists. So, alright, so to evaluate the left hand limit as x converges to 2 from the left of f of x. Well, now, if I'm converging to 2 from the left, I'm going to use this piece of the function, so I'll put that in there. And notice that that is 4. I can just plug the 2 in for the x now. And the right-hand limit, alright, now when x is larger than 2, we have to use this piece. So I put that in. Now I can just plug the 2 in here for x. We get 2 plus 2, which is 4. Okay, so now we see that these two numbers, the left and right hand limits, are actually equal to each other. And so our full limit is going to be 4. So our full limit, that is equal to 4. We can also see this graphically over here. Here's the graph of what this function looks like. Notice as x is approaching 2 from the right, f of x is approaching 4. And from the left, f of x is approaching 4. That red dot is right on 4 now. And so, it also seems like our full limit should be 4, because no matter how we approach 2, we're approaching the same number. It's a single number. And so our full limit is the same as our left and right hand limits. And that's because our left and right hand limits exist and are the same number. Alright. So let's also note here, we can also go backwards and we can say, if the full limit exists for a function and is equal to L, then the left and right hand limits will exist as well, and they will both equal L. That makes sense. I mean, all this is saying is that f of x is approaching the single number L as x approaches c from the left and from the right. And so obviously, if by saying that, then that also means as x is approaching c from the left, f of x is approaching L, so the left hand limit is L. And as x is approaching c from the right, f of x is approaching L, so the right hand limit is L. So we summarize that with a theorem. The full limit as x approaches c of f of x equals L exists if and only if the right and left hand limits exist and are equal to that same number L. Let's take a look now at some examples, and I'd recommend that you try these on your own to evaluate them. So let's consider this graphical example first before we look at any analytical examples. So here we're given the graph of a function, and we just want to evaluate these limits that I have written over here. So first of all, let's take a look at f of 1. Now that's not a limit, we just want to evaluate f of 1 here based on this graph. Well, we see that f of 1, here's 1 on the x-axis. We have this filled in circle right here, so f of 1 is currently defined to be -1. Now let's look at the left-hand limit as x approaches 1 from the left. Well, if we think of letting x values move along the x-axis as we get closer and closer to 1 from the left, we would be moving along this portion of the curve right here, and the y values are going to be getting closer and closer to -2. So the left-hand limit is going to be -2. Now you can also see that by doing this. If I pick points along the graph here, keep an eye on the y coordinate of those points. So currently, let's say x is currently 0.26 and y is currently negative 2.73. And you see that as the x values get closer to 1, the y values are getting closer to negative 2. You see that? So there x is 0.92, y is negative 2.08, and we're getting closer to negative 2. The y coordinate is getting closer to negative 2. Okay. Now what about the limit as x approaches 1 from the right? Okay, so as we move towards 1 from the right, we will be moving along this portion of the curve, and you can see that as we move along this portion of the curve, the y coordinates are getting closer to positive 1. So the right-hand limit as x approaches 1 from the right is going to be positive 1. And you can also see that graphically like this. If I pick points here on that curve, watch the y coordinates. As the x values get closer to 1, the y coordinates are also getting closer to 1. So currently x is 1.14 and y is currently 1.03. And so you see the y coordinates are getting closer to 1. Currently y is 1.008. Alright. Now what is the full limit? Well, the full limit, since our left and right hand limits here are not equal to each other, the full limit is going to dne. It does not exist. Now let's take a look at these down here. So what is f of 4? Well, currently you see f of 4 is that little filled in circle right there, and that is currently 1. So f of 4 is 1. What is the limit as x approaches 4 from the left? Well, as we approach 4 from the left, the function values are getting closer and closer to this value. It looks like it's going to be about 2.5. Let's double check that. If we just move along the curve, let's keep an eye on what is happening to the y coordinates. As the x coordinates are getting closer to 4 from the smaller side, the y coordinates, currently my y is 2.359, they are getting closer to 2.5, yes. So we would say that that is 2.5, that limit. Now what about the limit as x approaches 4 from the right? Well, as x approaches 4 from the right, we would be moving along this portion of the curve. It also looks like the y coordinates are going to be getting closer to 2.5. Let's just double check that. Just pick points here along the curve. Currently x is 4.65, y is 1.85, and it looks like the y values are getting closer to 2.5, and there we go. So the limit of the function as x approaches 4 from the right is also 2.5. Now since the left and right hand limits are equal to each other, the full limit will be that same number, which is 2.5 in this case. So that's a quick graphical example of partial limits. For this example, let's take a look at the limit as x approaches 0 from the right and from the left, and the full limit for the function x divided by absolute value x. You can try this one on your own. Pause the video. I'll assume that you tried it on your own, so let's go over the answer. Before we answer these three limits, let's note that x divided by absolute value x equals 1 for x larger than 0 and negative 1 for x less than 0. Now that's true because if x is positive, then the absolute value of x is just x itself. So for x positive, you're looking at numbers like x over x, which is just 1 because the absolute value is just x because it's already positive. For example, 3 divided by the absolute value of 3, that's 3 over 3. and that's just 1, right? On the other hand, if x is negative, then the absolute value of x is actually negative x, right? Because negative of a negative will make this positive, and this is equal to negative 1. For example, negative 3 divided by the absolute value of negative 3, well, that's negative 3 over 3, and well, that's negative 1, you see. All right? So that's why we have 1 and negative 1 here. This was 1 right here as well. Okay. Now let's answer these three limits. So first of all, let's take a look at the right-hand limit. All right, well, as x is approaching 0 from the right, that means we want to use this piece of our function. So it's going to be the limit x approaches 0 from the right of 1, and of course that is 1. So there's our answer for that one. Limit as x approaches 0 from the left of x over absolute value x. X approaches 0 from the left of negative 1, because now we're going to be dealing with this piece. And of course that is negative 1. And so our full limit, well, that's going to d does not exist, because these two numbers, while they do exist, they are not equal to each other. So the full limit cannot exist. All right, and graphically over here, you notice that as x approaches 0 from the right, my function value, the red dot on the y-axis, stays at 1. So the limit is 1 as x approaches 0 from the right. And then from the left, the red dot always stays at negative 1. Limit as x approaches 0 from the left is negative 1. All right. Let's take a look at another problem that you can try. Try this one. Now we have a piecewise defined function here. Square root x plus 1 plus 4 for x larger than 3. X plus 1 for x between negative 1 and 3. And then negative x squared plus 2x plus 3 for x less than negative 1. Now in the upper right hand corner of your screen here, you'll see a nice graphic illustrating which function to use for various values of x along the x-axis. Now we have three parts here we want to answer. First of all, what's f of 3 and f of negative 1? That's just testing, making sure that you know how to where to put these numbers, 3 and negative 1, into this function. What piece do you put them into? Alright, so let's do part A first. And by the way, I recommend that you pause the video and try this one on your own. So assuming you've done that, let's take a look at part A. Well, looking back up here, you see when x is equal to 3, I'm supposed to use this piece of the function. So that's going to be the square root of 3 plus 1 plus 4, and that is 6. Similarly, f of negative 1, let's see, I look through here, right here, when x is equal to negative 1, I use this piece. So it's going to be negative 1 plus 1, or 0. Alright, so there's my answer for part A. Now part B, let's see, the right-hand limit. Okay, so if x is approaching 3 from the right, let's see, then I'm going to use this piece of the function. So it's going to be the square root, x plus 1 plus 4. And now, because this is a well-behaved function, I can just plug that 3 in for the x. Plus 4, square root of 3 plus 1 plus 4. And that's going to be 6, right? Square root of 4 plus 4, 6. The left-hand limit, alright, that's going to be the limit x converges to 3 from the left. Alright, now, if x is converging to 3 from the left, that means x is a little bit smaller than 3. Now, which piece of the function up here do I use? Let's see, for x a little smaller than 3 right here, we want to use this piece of the function. So that's going to be x plus 1. Now, since this is a nice well-behaved function, I can basically just plug the 3 in for that x, and I get back 4. Alright, then the full limit of f of x, well, that's going to dne, because my left and right hand limits, while they exist, they are not equal to each other. So the full limit cannot exist. Alright. Now let's take a look at limit as x approaches -1 from the right, left, and the full limit. So let's see, we'll do that up here. So part C, limit x approaches -1 from the right. Alright, now if x is approaching -1 from the right side, that means x is a little larger than -1. So once again, we will want to be using this piece of the function again, the middle part, because that's where, when x is a little bigger than 1, we should, -1, when x is a little bigger than -1, we should be using this one. So it's going to be x plus 1. Now I can just plug the -1 in here for x, and I get, and that is equal to 0. Alright, now let's take a look at the left-hand limit. X converges to -1 from the left. Alright, now which piece of the function should we use? Well, when x is a little smaller than -1, we should use this one. Alright, that's when x is a little smaller than -1. So we'll put that in. So that's going to be x squared plus 2x plus 3. And now I can just plug -1 in for the x's here, because this is a polynomial, nice well-behaved function. Minus 2. 2 times -1 is minus -2. Plus 3. And, oh, I have a small error right here. I should have a negative right here with that x squared, right? Negative right there. See, I have a minus here. Forgot my negative, put that right there. So this is -1 squared minus 2 plus 3. And so that's equal to -1 minus 2 plus 3, and that is 0. Okay, so notice now that the right-hand limit and the left-hand limit down here, they exist, they both exist, and they're equal. And so the full limit as x approaches -1 of this function will exist, and it will equal 0. Alright, so there you go. We've answered all of our parts over here. Now, let's take a look at this graphically just to verify what we've done over here. Let's just pull up, here's the graph right over here. So as x approaches 3 from the right-hand side, notice that red dot on the y-axis. That's approaching 6, right? So we're verifying here this answer. And then as x approaches 3 from the left-hand side, the left, looks like my function values are getting closer to 4 right there on the y-axis. So that's verifying this right here. And so because those are not the same, the full limit down here does not exist as x approaches 3. And then at -1, notice how the limit as x approaches -1 from the left, the function values are getting closer to 0 on the y-axis right there where my pointer is. And as x approaches -1 from the right, the function values are also approaching 0. You see, basically the graph, even though it has a break at -1, even though the function is piecewise defined at -1, it does not have a break in it along the y-axis. So the function matches up. All right, so our left and right hand limits exist and they're equal. Whereas over here at 3, the function has a break in it. Okay, so the left and right hand limits exist, but they're not equal. Okay, and so we see that at -1 we've illustrated that our right hand limit is 0, our left hand limit is 0, and so our full limit as x approaches -1 is 0. And so that illustrates what a partial limit is, and that concludes this video.